equilibrium. So when we are talking about this complex ion equilibrium, often we're talking about it in terms of increasing the solubility of an insoluble or slightly soluble salt. And so you're going to see that kind of thing taking place in what we're thinking about here with these complex ions. So they're solubility related. The other thing is that this we're going to do some Lewis acid-base chemistry, and you don't necessarily have to be able to move the electrons around and see all of that, but that is essentially what's happening here. We have a Lewis acid-base reaction taking place. So calling back to chapter 16 on that. So what happens is that we can have a metal ion that forms a coordinate covalent bond with other molecules. Okay, and a coordinate covalent bond is one in which the electrons come from one atom or one species. So if you don't recall that terminology, I think that's semester 1 type of material. So in the cases that we're going to be thinking about, we're going to see that anions are going to donate the electrons to the cations. And so we're often going to see a metal cation whose solubility is increased by adding a molecule that it can react with and form this complex ion. So the complex ion is essentially a very large type of molecule, or larger type of molecule than what we've really been working with. Oftentimes we write it in its formula in brackets, or parentheses are fine, and then it's going to have a charge. So it's an ion, it's going to have a charge. So in this case, the silver ion is the Lewis acid, and the ammonia is the Lewis base. So if you recall, Lewis acid accepts electrons, so those electrons are coming from the ammonia. That lone pair of electrons on the nitrogen are being donated to the silver ion. So you'll also notice that there are equilibrium arrows, and because there are equilibrium arrows, we need to have an equilibrium constant. We're going to look at 2K. Two different, they're still equilibrium constants. We're just going to add some new subscripts to them. So we're going to have K sub D, which is the dissociation constant for a complex ion, and K sub F, which is the formation for the complex ion. Okay? So these are the reverse of each other. So K sub D is equal to 1 over K sub F, and vice versa. Okay. Because the dissociation, this is actually down here, we're going to have our complex ion in equilibrium with ions on the product side. So now we see how much this complex ion can dissociate. Okay. And then for the formation, it's the reverse reaction. And so that's shown here. So this is formation, and this is dissociation. And so the formation, we take the two ions, those are now the reactants, and we figure out how or what their equilibrium is with the complex ion. Okay? So really what we're going to see, one of the main takeaways is that if we have a slightly soluble salt, like AgCl, we put it in solution, we form the silver ion and the chloride ion. If we add ammonia, the ammonia is going to increase the solubility of that silver chloride. So when you can form a complex ion with a cation from a slightly insoluble salt, like the silver in this case, you're going to increase that salt's solubility. Okay? We're going to look at some examples of that and why that is. Okay, so let's look at this example first. We're going to take a nickel nitrate compound and dissolve it in 1 liter of water. All nitrates are soluble. Okay. It's also going to contain 1 mole of sodium cyanide. And we want to know what the nickel concentration is after this complex ion is formed and we come to equilibrium. So the complex ion equilibrium is we'll have 1 nickel 2+ ion plus 4 Cn minus in equilibrium with the nickel complex ion. And you'll notice in this case that ion has an overall 2- charge. Okay. This has a formation constant of 1 × 10⁻31. So it strongly is on the product side. So it's really likely to form products in this case. And so we want to figure out, after this reaction happens, when it comes to equilibrium, how much nickel ion is left in solution. Okay? So we're going to do this in 2 steps. And I do think this is slightly different than what your textbook does, but I think this is a little bit more clear. I think they're doing the same thing, they just don't explain it this way. So the first thing we're going to do is assume that all the nickel reacts completely with however much Cn minus and forms as much complex ion as possible. Okay, so we're going to assume that the reaction goes to completion. And we're going to figure out then how much product is formed, how much reactant is left over, if any. And we're going to do that with the BCA table, so we're going to need to use moles. Okay, same story as before. After we do that, we've formed as much complex ion as possible. We're going to take that amount, we're going to reverse the reaction and see how much ion is formed when we allow equilibrium to take place. So then we're going to do step 2, which is set up an ice table. And again, use molarity. Okay. Whoops. Oh, I did this thing again. Okay. So let's do the first step, which is to assume that the nickel reacts completely to form the complex ion. So we're going to take the nickel 2+ ion plus 4 Cn minus, react completely, so single arrow towards the products, to make that complex ion. Okay. In the problem, we are given moles that were used of reactants that are used to make this product. We start with 0.1 moles of nickel nitrate. There's 1 nickel nitrate in this formula, so we have 0.1 moles of nickel. For the Cn minus, we use sodium cyanides, and there's 1 Cn minus per formula unit. And so we had 1 mole of that. So we'll start with 1.00 moles of Cn minus. Everyone okay with that? And nothing to start with products. As we do the BCA table, okay, we need to use our stoichiometry. And the nickel in this case is going to be the limiting reagent. You can go through and work that out if you need to. So we're going to subtract 0.1 moles from the nickel and 4 times 0.1 from Cn minus. Okay. and we're going to form 0.1 of the product. Okay. So I use the limiting reagent moles, the number of moles from that, drop down the stoichiometry, and add it or subtract it as needed. Okay. So then after this reaction is complete, we're going to have 0 moles of nickel. We're going to have 1 minus 4 times 0.1, which is 0.6 moles of Cn minus, and 0.1 moles of the complex ion. Okay. Questions on the BCA table? Okay. We're going to take the output from that BCA table and use it now in an ice table. So we're going to take the nickel. We're going to put the nickel complex ion on the reactant side. Okay, we're going to say we've formed the maximum amount of the nickel complex ion. We're going to take those number of moles, convert it to molarity so we can use an ice table. And given those number of that molarity to start with, how much nickel is going to be left over? Because we said in step 1 that we used up all the nickel, but there's an equilibrium. Okay, so in reality there is going to be some amount of nickel ion present. Now they're down here. It's exciting. Okay. So we're going to use our ice table. Because we're in 1 liter of solution, the moles to molarity calculation is easy. We're going to end up with the same values. So we're starting concentration of the complex ion is 0.1 moles per liter. We have 0 moles per liter of the nickel ion, but we still have some of the Cn minus in solution because it didn't go away. Like there's still some left over from that BCA table, okay? And that's 0.6 moles per liter. Everyone okay with that? Okay. So then we'll do our normal ice table routine, minus X for the reactant, plus X for the nickel ion, and plus 4X for Cn minus. So then at equilibrium, we're going to have 0.1 minus X for the complex ion, X moles per liter for the nickel, and 0.6 plus 4X for the Cn minus. All right, so now we're going to put this into our equilibrium constant expression. We were given K sub F, so the formation of the complex ion. But we need to know the dissociation because as you see, our equilibrium is for the dissociation of the ion, not for the formation. Okay, so we're going to calculate Kd, and that's going to be equal to 1 over K sub F. And K sub F is 1 times 10 to the 1 times 10 to the 31st. So that gives us 1 times 10 to the minus 31. And we can set that equal to the concentration of products over the concentration of reactants. So we'll have in the numerator X times, in parentheses, 0.6 times 4, or plus 4X raised to the 4th divided by 0.1 minus X. All right, everyone okay with that? Now, the good news is we're not going to need to solve something to the power of 4, okay? Because our value for K sub D is very, very small, times 10 to the minus 31. And so any amount of X is going to be really tiny, especially in comparison to these concentrations that we're adding or subtracting from, okay? So we're going to be able to ignore this 4x and this x. Okay? So we're going to have 1 times 10 to the minus 31 equals x times 0.6 raised to the 4th divided by 0.1. And that's a much more approachable calculation. Okay. And so again, we'll solve for x just like we do with all of our equilibrium type problems. And we're going to get x is equal to 7.7 times 10 to the minus 32nd moles per liter. So a tiny, tiny amount of nickel ion left in solution. Okay. Questions on that yet?
So you have, like, at the top it's 1 times 10 to the 31st.
Yes.
And you write it as to the negative 31st.
Yes, so the value that we're given at the very top is the case of f value.
Oh.
And we need to do the case of d, so it's 1 over that value.
So for when you said that we didn't have to worry about the x's in the equation for the dissociation constant,
Yeah.
is that like you basically put the 0.6 over that and check if that's greater than 1,000?
I think that will still apply, yeah.
Okay.
Yeah. I will say that there's very few occasions where we're going to need to use the x, especially when you get a tiny, tiny k value. If your k is to the minus 3, that's when you need to start worrying, if we want to start thinking about it that way. Yeah.
Why can't you just use the ice table at the beginning?
So the question is, why can't you just use the ice table at the beginning? And the answer is that we hadn't calculated how much complex ion was in solution. So if you want to calculate that without the BCA table, that's totally fine. But you need to know the concentration of complex ion that could form.
Just make it max.
I don't think that's going to work. I don't think that's going to work. I don't have a mathematical reason to tell you, but I bet if I worked it out, I could figure it out. Yeah.
Could you explain why you did not set out the equation
Why I didn't use the formation? Yeah. So again, when we're thinking about how we're approaching these, we need to think about how much complex ion is possible to form. So we need that sort of maximum value, that limiting value, and then we need to figure out, like the easiest approach is then to figure out the equilibrium from that point. So could we have done it with the reverse reaction? I am not sure. This is the approach that will work best because we want to figure out how much nickel ion is present after we allow it to dissociate. So it's sort of a thought process of going through, okay, what can form by to completion, reaction goes to completion, so that's the BCA table part, and then what is possible in terms of the equilibrium. So in that case, it's best to reverse the reaction and figure out the ions that could dissociate. Yeah. Other questions? Okay. So I have said already that complex ions are going to affect the solubility. So here's a nice example with the silver chloride. This is the written out version completely now that I alluded to before. So if we look at the solubility of silver chloride in water, has a KSP of 1 times 10 to the minus 10. If we were to figure out the molar solubility or the concentration of each of the ions present in solution without sort of adding anything other than water, we would get 1.3 times 10 to the minus 5. Okay, so that's just KSP equals x squared and that sort of thing. So then what happens than if we add ammonia to this solution. If we add ammonia, the silver ion can react with the ammonia, that's the Lewis acid-base reaction, to form this complex ion. And it has a pretty big formation constant, 1.6 times 10 to the 7th. So that reaction does occur to a good extent. And what we can see is that if we had some of this in water and we added some ammonia, the ammonia and the silver are going to react, which removes some of that silver product from this solubility equilibrium. And just like we saw with Le Chatelier's principle, that forces the reaction to go towards the product side, which increases the solubility of the solid. Okay? So again, this is just Le Chatelier's principle. We're reacting some of the product of our solubility equilibrium with another compound, with the ammonia in this case. So that product is removed from the solubility equilibrium, which shifts the equilibrium towards the product side, which says that we have increased the solubility of the silver chloride salt. Okay. 1.3 times 10 to the minus 5. So let's say we want to then determine the molar solubility of silver chloride in 1 liter of 1 molar ammonia. Okay? So we have 2 equilibria in play. We have the solubility of the silver chloride, and we have the formation of the complex ion. So our KSP for this silver chloride is 1.8 times 10 to the minus 10. And for the formation of the complex ion, our K sub F is 1.7 times 10 to the 7. Okay? So our first step here is to write an equilibrium reaction that incorporates both of these equilibria. Yes?
This is a silly question. If AgCl is insoluble, how does it have a solubility?
Yeah. So we say it's insoluble, but there's some amount that goes into the solution. It's one of those we've lied to you in the past. Now we're correcting that. Okay. So that's why I keep saying insoluble or slightly insoluble solid. Okay, yeah, good question though. So we need to combine these equilibria because it's much easier to work with one equilibrium equation than it is to work with 2. And we can do that, and we've seen how to do that in chapter 15 when we were adding up chemical equations. And so if we add these 2 chemical equations, what we're going to see is that the silver ion cancels, and we're going to get silver chloride solid plus 2 ammonia. I don't want that. I'm going to leave off the Lewis dots. In equilibrium with Cl minus and the complex ion H3N Ag and H3 plus. Okay. How do we find the K for this overall reaction? Good.
Do you just take the concentration of the products over the concentration of the reactants?
We will do that eventually. But we now just want to find a new K for this overall reaction. Think back to chapter 15. Yeah. Exactly. It's because we've added these 2 equations, equation 1 and 2, to get the overall K. We're going to multiply the Ks for the individual reactions together. So we're going to have KSP times K sub F. Okay, and so it's 1.8 times 10 to the minus 10, 1.7 times 10 to the 7th, and we'll get a K value of 3.1 times 10 to the minus 3. Okay, so remember when I just a few seconds ago said we weren't going to be able to ignore x's when our k's were this, about this magnitude? This is what I was thinking. We're going to not ignore x. This k doesn't necessarily have a subscript. That's just for bookkeeping. If you wanted to give it k overall works or k3 or whatever, yeah. Okay. Now we have a k for this equilibrium. Whoops, let's not do that. This equilibrium. Okay. So now we can figure out the solubility of the silver chloride when we also have ammonia present. And in this case, it's an ice table. No, we don't have to do a BCA table first. I'm going to rewrite my equation. Okay. And I can set up the ice table. Silver chloride is a solid, so we need to forget about that. Okay, that doesn't matter. We don't include solids in our equilibrium calculations. So I'm just going to draw the vertical line so I don't try to do anything there. Ammonia. Okay, we said that we are figuring out the solubility of silver chloride in 1 liter of 1 mole per liter ammonia. So we have 1 mole per liter of ammonia. And initially, we have 0 moles per liter of products. Okay. For change, we drop down our stoichiometry, minus 2x for the ammonia, plus x for chloride, and plus x for the complex ion. So at equilibrium, we're going to have 1 minus 2x for the ammonia, x moles per liter for the chloride, and x moles per liter for the complex ion. And now we can put these values into our equilibrium constant expression using the k value we just calculated. 3.1 times 10 to the minus 3 equals x squared divided by 1.0 minus 2x squared. So in this case, we aren't going to ignore x compared to the 1.0. I think it's actually on the border here. But the good news is we have a perfect square. So we can take the square root of both sides. Okay. Perfect square, take the square root of both sides. And we'll get 0.056 equals x over 1 minus 2x. And we'll solve for x and get x equals 0.0504 moles per liter. Okay, so what we've just calculated is the molar solubility of the silver chloride. Okay, so if you recall, when we calculate x, when we have a KSP, we calculate x, that x is equal to the molar solubility. Okay? So this is the molar solubility of silver chloride when it's in the presence of the ammonia. Okay, and you can see that its solubility is pretty high, 0.05 moles per liter. And if you recall, before we added the ammonia, the solubility was what? It was tiny. Okay. So you can see that this solubility increases for the silver chloride when there's ammonia present. Okay, and that's because it's able to form that complex ion. Does that make sense? Questions? All right.